get this party started, shall we? First things first, homework still in progress. I've answered the same question like 17 times, so I apparently did not write my instructions clearly enough. I will apologize for that, and for those of you who are going to ask me this question, I will clarify that enter the -2 log likelihood from a model predicting well-being after including these two effects of stress. I meant in addition to the stuff that's already predicting well-being in section 1. That's what I meant. So next time I will write that out more specifically. I apologize. The idea of this homework is that you're always adding things. So the only point at which you go backwards is just above this to do an empty model for stress to see how much of it is between versus within. So any other questions that I can answer for you? Let's see, Heather. Okay, how do you think you are doing it? Estimate plus or minus 1.96 times, and it would be the square root of the variance, right? So yes, that is the right formula. Now the question is, what is the estimate and what is the variance that you're putting in? The estimate of the within person stress main effect? Yes. So that's going to be the center of your interval. That's the fixed effect. That's what it would be on average. And what variance are you putting in? Ah, that is the problem. So you created a fixed effect confidence interval instead of a random effect confidence interval. So you created an interval for the estimate itself as opposed to how the slope varies across people. So your confidence interval would be provided by SAS, by the way. If you add CL to the model line as an option, it gives you those intervals. This it will not give you. So right idea, wrong thing. The variance in the within person stress effect is what you would put into the second part of the formula here. So it ends up being the standard deviation that goes with the random effect. And I don't have a macro for that. I'm sorry, you have to do that yourself, but it's only 2 numbers, so it's not so bad, right? Yeah. Other questions? Lindsay.
I'm struggling a little bit with section 31 and section 3, and whether that is, like, if that is an estimate that I'm getting, or if I'm doing some math to
Both. So total variance is code for total R square. So that is the correlation between the model predicted outcome from the fixed effects and the real one squared. So a lot of people, you can get this 2 ways. The easiest way is to just run proc core on the data set that you saved out PM to. That will give you the correlation. You then have to square it yourself to get R square. Otherwise, there is a total R square macro that you can use, and the phrasing in this, note the additional percentage of total variance. That's asking for the change in the total R square, which will show up in the macro, or you have to calculate it yourself relative to the previous. So. Other questions? All right, I've had a lot of interaction with folks about pseudo R square, so I wanted to do a little bit of review with that and how you know which variance component in your model should be targeted by a given fixed effect. So I wanted to do just an example based on the homework you're working on, and then an example based on these cross models that we're starting this week. Rather than drawing on the board, I'm going to attempt to draw in PowerPoint, which is how I make all of my diagrams. I make pictures in Excel and I make diagrams in PowerPoint. So let's have some shapes, shall we? Here's one. I'm going to add text to this. hopefully. Edit text, there we go. Once upon a time there was E variance, right? Residual variance. Let's make this text bigger so we can read it. There, that's good, right? All models start with that. E only, single level. Let's say that we're talking about the example from our current homework, which was also homework 8 from last semester. In our first step, we would take that residual variance and we would split it. So I'm going to label all of these things here within person, level 1 residual within person variance, and what's the symbol that we use for that? Do you remember? In notation, if I were saying what is the symbol that goes with level 1 within person residual variance, what do I use for that? Greek letter with the squared at the end of it? Which one's that? It's the E one, yeah. So I'm going to say variance of E, and then I'm going to put in here sigma squared, right? Sigma squared sub E, actually, right? And then this one, trying to put in all the words here, level 2, between person, random intercept variance of, what letter is this one? If it's not E, it's got to be the other one. Not a trick. What letter in the equation? Use. Use 0 specifically here. And what's the symbol I use for those? I do taus. Tau squared for any of those. All right, so we have here level 1, level 2 to start with. And then if we have a longitudinal model, for instance, we add in effects of time. I need a box for those. I'm going to make myself a time box here. Edit text. This is time and time squared. Make that a little bigger. Okay. Now the question is, which of those two piles should time and time squared account for as a fixed effect? So I'm using circles to denote variances, piles as it were, variance components, and boxes to denote observed variables that are going to have fixed effects. So which of these two should those two effects account for, time and time squared? If time is level 1, then which one does it go with? Residual variance. Now, I'm going to do this like it's like a Pac-Man eating part of it, like that. That's my sort of Venn diagram-y way of saying it's accounted for. Does that work for you? Why not, right? Now, the question is, what happens at level 2? It's either going to go up or it's going to go down. How do you know which it will be? Is based on what kind of variance time has in it. So let's say that we have a time variable at level 1 that is purely level 1, meaning it's no variance across people and when they started the study, so everybody has the same set of occasions. It's either balanced or very nearly so. If all of the variance in time is level 1, it should account for level 1 residual variance, but what's going to happen to level 2 random intercept variance as a result? If level 1 residual variance goes down, then level 2 random intercept variance goes up. They're yoked together. So you watch, it went up. It's a bigger circle now. Now what if this was assignment 2, where time had some between person variance in addition to its within person variance, meaning that people started the study at different points in time? then what do we need to do? Because if this time variable is not purely level 1 within, we can't have a single effect of it in the model, right? How do I fix it? What did I have you do in homework 2? Besides age, what did you put in your models? Cohort, yeah, which was the level 2 version of time. So because it could be any kind of time metric, I'm going to make that level 2 time. You could potentially have a squared effect of that. You didn't in that example. If cohort matters, then it should reduce the level 2 between person random intercept variance. So I'm squishing that back down here. So those are fixed effects of time. We can have random effects too. So if I add a random effect of time, first of all, can it be level 1 time, level 2, or either? Which of those two time predictors can have a random effect? Level 1, level 2, or either? Not meant to be a trick question. We got vote for 2. Level 2 time can have a random effect. Anybody want to vote for 1? I'm voting for 1. Yeah. Level 1 time can have a random effect because its effect is random over people. Each person gets their own time effect. In order for that to happen, each person has to have more than one value for time with which to create their very own slope. Each person cannot have a level 2 time random effect because each person would have only one value for age cohort. So this one, it can have a random effect. I'm going to put this over here. It's still level 2, it's still between person, but now we're going to say that this is time slope variance. And this would be, for instance, U1. Could time squared have a random effect across people? Sure, right? So let's make one of those. It's still level 2, it's still between, it's still random. And now it's time squared. Oh, try that again. There we go, slope variance. And it would be potentially a U2, still with the tau. So now our model has 4 different piles of variance. There's 4 potential R-squares for any given effect. But not all of them are going to be relevant. So then we added age at baseline. Yeah, question, Andrew? Sure. Time squared slope variance, yeah. Time squared slope variance. It is the random effect of level 1 time squared. So the fixed effect then is level 1. It has a variance across level 2 units. Yeah, everybody gets their own time effect and their own time squared effect. Yep, those variances are level 2 commodities, so they're up here. Other questions? Let me squish this a little bit. Yeah, go ahead, Jacinta.
So I guess in level 2, you said level 1 has the random effect.
Yes. So the level 1 predictor, meaning time within person, is it time 0, time 1, time 2, as opposed to the level 2 time predictor is where did you start the study relative to other people. The level 1 time predictor has an effect that varies over level 2 units randomly. So its fixed effect is level 1. its random variance is at level 2. And yes, that is confusing. Andrew.
For the notation,
Yeah.
can we call it L2 be random L1 times slope?
Yes, we can. Yes, we can. Level 2 between person random level 1 time slope variance. Yes. And that is actually not overkill, because when we get to 3-level models, level 1 predictors can have random slopes over 2 and 3. Level 2 can have random slopes over 3. So you conceivably could have a random level 2 time slope variance if you had a 3, as well as a random level 1 time slope variance. Yes. Okay, with me so far? I know. This is why we're reviewing, right? Because this stuff is hard. It's complex. So we then added another level 2 predictor for, I'm going to call this level 2, actually let's call this one group. Let's do that. Meditation group, right? By the way, the first time I made that homework, at some point halfway through, I stopped typing meditation and started typing mediation. So it became a mediation training group halfway through the assignment. Someone had to point that out. I didn't even catch it. So let's say level 2 group. In this case, group is level 2 because everybody's in one group or the other. If I add a main effect of level 2 group, which of my 4 piles of variance should it account for? I'll go through these one at a time. Can level 2 group all by its own, as my son would say? I do it all by my own. Or I do it by my own self. That's another one. Can level 2 group all by its own self account for level 1 variance? No, that doesn't make sense. So it's got to be level 2 group, so it's got to be one of the level 2 piles, right? Which one is it? Here's an easy way to tell. Do you see group by time in here? It has to be the first one, yep. Level 2 group is going to capture random intercept variance. Part of the reason why people start out differently may be the group they're in. So group moderates the intercept. So when you see a main effect of a predictor like that in your head, think of it this way. Group, it's a group by intercept interaction. That will help clarify which variance component it's targeting and what its role in the model is. Likewise, if we have level 2 group, let's throw in another level 2 covariate, let's say. Let's call it education. Why not, right? Based on what I just said, if I think of it as education by intercept interaction, nope, not that one. Nope, hang on. There. Where does it go? Yeah. What if I had level 2 group by level 2 education? So these are both level 2 terms. That means it has to be one of the level 2 variance components, right? What do you think? Goes to the same one, yep. This says that the effect of group on the intercept is different as a function of education, or that the effect of education on the intercept is different as a function of group. But all of them go up here. Now, what if I want to know if my groups change differently over time? Well, according to this model, the idea of change over time is expressed with two different terms, linear and quadratic time. So if I have group by linear time, let me make that more specific here, group by level 1 linear time, that's what's known as a cross-level interaction because it involves a level 2 variable and a level 1 variable. So in this model, it's not as obvious where it should go because it could go level 1 or it could go level 2 given that you've got a mixture of both. Now where do you think it goes? I see hands. The middle circle on the top, yes, because it's time. The middle circle on the top is all the reasons why the time effect differs across people. Maybe some of those reasons is group. Right. Likewise, what if group moderated level 1 times squared? Then which variance should that cross-level interaction predict? Top right, yeah, that one. Now what if, let me copy my slide here, go to this one. What if I didn't have a random quadratic time slope variance? What if that wasn't significant and so I didn't have it in my model? Now where does it go? So repeat the question. What if I did not have a level 2 between person random level 1 time squared slope variance in my model because it was not significant when I did a model comparison to test it in the first place? Now where does level 2 group by level 1 time squared go? Point of the debate, some people would say it doesn't go. That's what Amy's saying, she's shaking her head. That doesn't make any sense. But what if you put it in your model anyway? It's residual. Has to be. That's the only thing that's left. It has to be this one. If you think about where these random slopes came from in the first place, we started out by partitioning E into intercept variance, and then we partitioned the intercept variance into time slope variance. So it's as if that variance was never partitioned out to become quadratic time slope variance. But yes, if you have a cross-level interaction, more generally, the cross-level interaction explains the random slope variance that is associated with its level 1 predictor. Say that again. If you have a cross-level interaction, such as level 2 time by level 1, level 2 group by level 1 time, that cross-level interaction explains the random slope variation associated with its level 1 predictor. So if I threw in education by time, that explains time slope variance. If I threw in education by group by time, that explains time slope variance. This one? This one says that in the sample there is a rate of acceleration or deceleration, which is twice the quadratic. Your new level 2 term says that what that rate is needs to differ by group. And if you give each group its own rate, that should reduce the residual variance around the lines. So that effect would be what's known as systematically varying in this context. It's not that time squared is fixed. Everybody doesn't need the same. It's not that it's random. Everybody doesn't need their own. It's that some people need one and some people need another one. Time squared slope differs deterministically as a function of group, but not randomly otherwise. So you can call that non-randomly varying, or I prefer systematically varying. How are we doing? With me so far? See, it's easy to just say the rules off the top of my head, but how they actually play out is always context specific. So more generally here, level 1 predictors reduce level 1 residual variance. The main effects of level 2 predictors and level 2 interactions, meaning when both variables are at level 2, such as group by education, they account for intercept variance at level 2. Cross-level interactions account for the random slope variance at level 2 that is associated with its embedded level 1 predictor. Cross-level interactions whose level 1 predictor doesn't have a random slope then predict residual instead. That's this one right here. Ooh, come back. That one. So if time squared has a random slope, any interactions of level 2 variables with it explain that random slope. If it doesn't, then that cross-level interaction has to explain the residual instead. In the model that we were working with our assignment, we had a random slope here, so I'll leave that in. Add another box. Then in section 2, I asked you to add 2 new variables. Level 1 stress, which was person mean centered, and level 2 stress, which is the person mean centered at 5. So using the rules that we just went over in a general, how do we apply those to the specific? Level 1 stress, if I person mean centered it, it only has within person level 1 variance. Therefore, which variance component is it going to predict? If level 1 stress has only level 1 within person variance in it because I person mean centered it, it must predict residual. Yep, goes over here. If I account for residual variance, what's going to happen to random intercept variance? Goes up. Now level 2 stress. It has to be level 2, right? Because it's all by its own self. Does it have time in it? No. Does it have time squared in it? Nope. So what does it do? Intercept. Yep. Goes over here. Then I asked you to test a random effect of level 1 stress. So I'm going to have to start working my way around the page here. Level 2 between person random level 1 stress slope variance, which is a U3. And I asked you to test 2 new fixed effects, one of which is level 2 group by level 2 stress, and the other was level 2 group by level 1 stress. So group by level 2 stress, where does it go? I'll give you a hint. Where did the main effect of group go? That way. Where did the main effect of level 2 stress go? That way. Where does its interaction go? That way. See, it's more fun when you get some activity involved, right? I don't have a standing desk, so I have to improvise and find ways to get movement into my day. Now, here's a tricky one. Level 2 group by level 1 stress. It's cross level, so it's not as obvious. So what's the rule? It's level 2. A cross-level interaction explains the random slope variance at level 2 associated with its level 1 term if present in the model, or residual variance otherwise. So which case is that? The former or the latter? It's the former, yeah. It's the thing we just added. Part of the reason why some people have a stronger effect of stress than others might be because some of them got mediation training and others didn't. That was a joke. Yeah. Thank you, Claire. She's laughing. Now, what if we did not have that within person level 1 stress slope be random? It would go to residual. But if this random slope is needed in the model and you don't have it, then this effect would not be tested accurately. It would have way too high of a type 1 error rate without that. The standard error for its term incorporates that slope variance in it, and it makes it bigger. So to the extent that the slope variance is present, it needs to be included in the model before testing things that would explain it. And I think this is about where we left off. This is the end of your homework 3. Questions? All right, let me do the example from the chapter 12 / my 2007 paper, finally publishing my master's thesis data, albeit from a perspective I never would have expected. So I'm going to change the notation here. Level 2, person random intercept variance. Level 2, item random intercept variance. Get my predictors out of the way here. So the story in chapter 12 is that I have the same people measured on response time to 50-some pictures. So we started off with a single level model where it's E only, added a level 2 person random intercept, and then added a level 2 item random intercept. And then we started adding predictors. I started with an item predictor, which I think, I don't know if I started with it, but I know it's in there, item salience. Level 2 item salience, let's say that. Now, where does that one go? Top right, it's an item thing. So it explains why some items have different intercepts. Then I added level 2 item, I think I called it meaningfulness. Might have been relevance. I go back and forth with those two terms. There. Where does it go? Same place. It's an item thing. Then I added level 2 age, which actually had 2 variables in it for age group plus years over 65. Where does that go? Is age a people thing, an item thing, or a trial thing? People. So where does it go? Over here. Then we get into cross-level interactions. or interactions of various kinds. Let me do one of these here. Level 2 item salience by level 2 item meaningfulness. Where does that one go? Right here, right? An item thing times an item thing has to be item variance. What if I had level 2 age by level 1 item salience? Let me add this person age more specifically, since we said that's what it was. Now, where that goes is going to depend on what else is in the model. At this point, I had previously added a random effect. Let me move my item things over here just a second. Items need to move over a little bit. They go over here. I added another person random effect, level 2 person random item salience variance. Move age over here. So given that that's in my model, where does this thing go? Level 2 person age by level 1 item salience. This is tricky, right? Because it's like, well, it's level 2 person is definitely a person thing, but then I have level 1 item, so does it go on the item side or the person side? Or is there an interaction somewhere in the model that it can go on?
So does there have to be either an interaction circle or it would be in the bottom?
And there is an interaction circle. That's this new one right here. Those are people differences in how salience affects their performance. Salience is an item characteristic. So people differences, some of which might be due to age. So salience is an item characteristic whose effect can differ across people. Likewise, I could have a people characteristic whose effect could differ across items, but not in this story. Another interaction that I did was level 2 person age by level 1, or not level 1, darn it, this is 2. This is 2. See, I think I like drawing by typing a lot easier. It's a lot easier than erasing. Item meaningfulness. Where's that one going to go? Is there a term in the model that says that people get to differ in the effect of item meaningfulness? So where's it got to go? Residual. Yep. And likewise, if I fit the three-way interaction of age by meaning by salience, that goes on residual too. How are we doing? Does this help? Question?
So if there was an interaction for person random item series level 2. So would that level 2 person age and level 2 item meaningfulness go into that circle on level 2, and then but the item salience and person age would stay in the residual because there's no
Yes, yes,
Okay.
exactly. So what you said, for folks who aren't going to hear you at home here, is that if there was another level 2 person circle here for meaningfulness, then this term would have gone over there for that one. But I would have to have a meaningfulness by salience random effect for this three-way interaction to have accounted for that. Otherwise, it sticks on residual. It is possible. You can have random effects of interaction terms. I've never gotten one to estimate in real data. It's theoretically possible. Same rules apply. You have to have the main effects that underlie it both be random, and then you could have the random interaction term. And by the way, that idea is the keep it maximal idea would dictate for this design, is that you should have all possible random effects so that all of your cross-level interactions are targeting random slope variances. That's the keep it maximal paper that I gave you to read. That's their opinion. I say you keep the ones you need and then you let explain residual variance otherwise. But the jury is still out on that. Other questions? So what if, let me back up to this picture here, and let me get rid of level 2 stress. Let me go back to where I was when I added level 1 stress. So this is the previous example, longitudinal, time and time squared as my level 1 predictors, each of which has a random effect, level 2 predictors of education, group, and now I'm asking what would happen, this isn't here yet, if instead of person mean centering stress, I just put it in all by its own grand mean centered, without the level 2 counterpart. What is that called? Smushing. It's called wrong, that's what that is. This is a conflated effect. And remember the dead giveaway number 2 that I gave you to know that someone's done this? If there's no level 2 counterpart in their tables or their story, that's the first part, but the second, if that level 1 variable of stress, I'm thinking of it as level 1 because it's measured at each occasion, if it still has its level 2 variance in it, and I don't have that level 2 stress variance elsewhere in the model, it's still going to account for residual variance because that's the level 1 part, but what else is it going to do? The level 1 variance would be reduced. Level 2 is going to be reduced as well. So even though I'm labeling this level 1 stress, it's actually both. To the extent that that level 1 stress variable has an intraclass correlation greater than 0, it has between person variance in it. Therefore, when I think about pseudo R-square, the level 1 part of it is going to account for level 1 residual variance like it's supposed to, but the hidden level 2 part of it is going to account for random intercept variance at level 2. So if a level 1 predictor explains level 2 random intercept variance, that's your giveaway, that it's not really just a level 1 predictor. The level 2 variance that it explains, though, is likely to be incorrect because using this same box in both places says that its fixed effect for its level 1 variance is the same as its fixed effect for its level 2 variance. Unless that is exactly the case, the pseudo R-squares that you get to go along with that are going to be wrong. Do I want to say that again? Maybe? Yeah? Okay. So back up here, right? Make these go away again. So this thing right here, I'm calling it level 1 stress because it's time varying, but to the extent that it has an intraclass correlation greater than 0, that means it has between person variance in it, so it's really level 1 and level 2. The level 2 part is why are some people higher in stress on average? The level 1 part is why is today higher than my average or lower than my average? So because there is level 1 variance in stress, that level 1 variance is going to account for level 1 residual variance like it's supposed to. And that's this part here. Let me make that red. But because it also has level 2 variance in it, it is simultaneously going to account for level 2 random intercept variance. Its level 2 part is going to do that. But it's going to do that incorrectly to the extent that you can't represent 2 different kinds of effects of stress with 1 variable. When you smush, when you put in 1 predictor at level 1 without putting in its level 2 counterpart, you're saying the within level 1 and between level 2 effects are the same. If that's not the case, then this pseudo R square for the intercept part for the level 2 is likely to be incorrect. But we can fix it. All we have to do is bring back the level 2 counterpart. Level 2 person mean stress, which was also grand mean centered. Where's that going to go? It is going over here with all its buddies. Hang on. All right, there. So it's going to pick up the difference. It's going to pick up the level 2 effect in total. The extra level 2 effect, that has a special name. Starts with a C. Contextual, that's what it's going to pick up. So part of the level 2 effect was already there because it was in the smushed part of level 1. Adding the level 2 mean picks up the remainder of what should be the level 2 effect to get to the total of the level 2, the total between effect. So the level 1 effect and the contextual added together get to be your total level 2 between. And I find that confusing, which is why we don't do it this way. But I want you to know how and to understand it well enough to make your own decision as to when it does or doesn't make sense to do it this way, to have contextual effects instead of between effects. All right, other questions or things you want to hear again? So in reading your quiz answers, I want to take a second just to clarify the difference between variance and effect. Any predictor that has an intraclass correlation greater than 0 has at least some between, and any predictor that has an intraclass correlation less than 1 at least has some within. So there has to be variance of that kind before that variance can show an effect of that kind. So if you put in this level 1, level 2 stress variable and it's not significant, that doesn't necessarily mean anything about its variance, what kind of variance it has. It just means that variance doesn't have an effect. The variance is a precursor. And so that's what we want to worry about when you're thinking about where do the predictors go in your model. At what levels do they have variance, not just at what level is it measured. And we'll see this in greater detail when we get to 3-level models, in which case you have to worry about 3 different levels of smushing potentially for level 1 predictors. Okay, other questions or things you want to review? And if at this point you're looking at this and going, I have to write all this up, how am I going to explain this? I can barely keep it straight in my own head. How is anyone going to follow this? This is where your friend total R square can save you. There's one of them, right? The square of the correlation between your real outcome and the one predicted by the model, putting all the piles back together again. That can be more understandable and easier to track in models that have large, many sources of variance components. So that's why I make you do both in your assignments, so that you get practice and you can decide for yourself which is more useful. Sometimes I do both, sometimes I do one or the other. Pseudo R square is specific. Of this kind of variance, how much did I get? Total R square is general. How well does my model work? So they're complementary sources of information. The example that I have for today is actually a good case of when total R square would look really, really bad. So would you like to see this one? It has a story. You know they all do, right? That's the nice thing about having been in this game long enough, is that I have so many real data sets to show you where things don't work out perfectly, which is all the kind of data that you actually have in your lives, right? You don't have perfect data. So this was yet another person who learned the hard way never to ask me to be on your committee unless you want to do more work. Just saying, right? Right? She's like, I know, I hate you right now. But this was going to be his master's thesis. And so this is a student, he just finished a postdoc and he's going to be starting a new tenure track job. So his happily ever after. Part of his sales pitch, by the way, is that he's not just a cognitive psychologist with lots of skills in eye tracking and neuroscience and attention, but he knows how to do the fancy modeling that goes with it. So he got to have a job. So yay, Mark. But this was his master's thesis. And at the time, he didn't know any of this, and he was going to do repeated measures ANOVA. And I talked him out of it, and we ended up working on this paper, and it got published. And so it's a nice little piece, and I wanted to show it to you as an example of how we can use the cross models. The issue was that he wanted to look at how eye movement characteristics changed over the course of looking at a picture, depending on what the instructions were for what you were supposed to do while looking at the picture. And eye movements, as you might imagine, are unbalanced, right? Everybody moves their eyes at different rates to different places whenever you feel like it. And he wanted to look at how these eye movement characteristics changed over the course of viewing. And his original plan was to carve up the 6-second interval into 12 500 millisecond bins. Why? Why would you do that? Because repeated measures ANOVA needs factors, right? You're nodding, right? It needs factors. And I said, okay, so what are you going to do if someone starts moving their eye in bin 9, but they don't stop moving it until bin 10? Where does it go? And he's like, and how do you know that 12 bins is enough? Why not 30? He's like, yeah, so, but you know what this is, folks? This is a growth model. He has time, it's just that it's within 6 seconds. But because the technology is such that he has up to the millisecond resolution in what's going on, he can actually analyze eye movements specifically, regardless of when they started and stopped, and each person can have their own set of eye movement data. So these are 53 subjects, introductory psychology students, doing this for a long time. 67 natural scenes. Everybody saw the same pictures, and there was a total of almost 61,000 observations in this data set, because we're literally analyzing every single eye movement that these people made. These models, by the way, if you have data that take up this many rows, does anybody work with data sets on that scale? No? Nobody has to? Well, this is good, because you know how long these models take on 60,000 observations? They can take a while. There is another package within SAS that I don't know has an analog in other programs called HP Mixed, by the way, High Performance Mixed. The code is exactly the same, and it goes way, way, way faster. It has computational efficiencies built into it that are made to work with large data. So if you're ever in this position, type HP in front of your mixed, and it may go a lot faster for you. And you can look that up in the manuals. So we're looking at how two different outcomes, fixation duration and saccadic amplitude, vary over time as a function of what the people were supposed to do in looking at the pictures. So group in this case is a 4-level variable that's between subjects. Everybody looked at the pictures either with an instruction to do just free view, memory. They thought they were going to have a memory test afterwards. They didn't, but it was just a trick. They were scoring the pictures on how pleasant they thought in the third condition, and the fourth condition was a search for an object that was impossible to find. So they're all doing different things while they're watching the picture, and we're looking at fixation duration as an outcome. Now, I created 3 different versions of time here, and you'll see why I did that later on, but these are centered at different places. 1 second into the picture, 2 seconds into the picture, or 5 seconds into the picture. So somebody may or may not have an eye movement exactly at those points. So these are predictions across the 6 total seconds. So here's my first model, E only, 1 pile of variance. So this is all of the variation in fixation duration in 1 pile. On average, people fixated for 256 milliseconds. We then added a random intercept for subjects, and it works out that the intraclass correlation then after doing so is that it is only about 6% between subjects. So does anybody know anything about eye movements? Anybody? No? So I can just make shit up with the Mandan like usual? No one's going to correct me? Okay, well, I thought that was sort of cool, right? All of the variation in this story is within people, it looks like. 94% has to do with what's going on while you're looking. That's the part that most of these analyses would have either aggregated over or gotten rid of. Some kind of mean fixation duration would have been analyzed instead, resulting in a loss of 95% of the data. So then we added items, because since everybody is looking at the same pictures, some pictures may have longer fixation durations than others because of whatever characteristic of the picture we have. So we add a random intercept for items, making this 2 different level 2 units, persons and items. And the part of variance for item is tiny. It works out that it is 0.3%. So these items did not really differ from each other in average fixation duration. So in total then, I have this breakdown for you. So the total in this denominator is just from summing these 3 numbers together. You can do that when you don't have random slopes. There are no covariances among these variance components, so you don't have to worry about how you combine them. So you can add the person intercept variance to the item intercept variance back to the level 1 trial specific variance, and it works out that 6% is between subjects, 0.3% is between items, and 94% is something else. Now, we don't have any item pictures, any item predictors in this case. He didn't care about the pictures. He just needed them to look at something. So I'm not going to get that 0.3% back, ever. The one manipulation, though, remember what it was, which group you're in? That's a people thing. So if he had the most perfect model in the history of the world, and his people predictor was the strongest thing ever, what is the best R-squared that could come out of this story right now? %. People differed from each other 6%. That's the only kind of predictor that he has. So this is an instance in which total R² is going to look horrific because most of the variation is in places where we don't have any predictors. So we couldn't get it anyway. So should it be counted against us? I don't think so. So just like we do in other kinds of longitudinal data, I wanted to make a picture. So here is a rounded version of time so that I could get a saturated means model in which each condition got a different trajectory. I saved those condition means to a data set, and then I made a picture. So here's a proc Gplot. You can customize every aspect of your picture, and this is what the trajectories look like. Now there's a lot of noise in this first part. Note that I rounded viewing time into these bins. This is what he wanted to do for his ANOVA. I used the same 12 bins that he did, but I just wanted a picture. So if you look at that shape, disregarding a little bit of the noise here, what does that shape look like to you? A little bendy, a little quadratic-y, I think. It does look like there's some intercept differences between his lines. There may be some slope differences as well. So that's what we fit, was quadratic time. So rather than putting in hard-coded time predictors, I put in placeholders. Do you remember the file save thing that I made you guys do when you're learning SAS? Same idea here. I created a new programming variable, just called time, and in this analysis, I set it to be the version where we have centered it at 1 second. So I have ampersand, the programming variable, and a period behind it that is to be replaced with fixed time at 1 second here. I added quadratic, and this line you guys haven't seen yet. This is the parm statement. This is a means by which you can provide your variance parameters with starting values to make the model go faster. So most programs have a way to do this if you know how to ask for it. These values came from my previous model, and the list that you give it on the parm statement is in the order that it shows up in these tables. So make sure that you're following the same internal order that SAS uses when you list the values. So I'm doing this just to get the thing to go faster, because with this much data, these models can take a while. So it does look like there is significant change at level 1. So this is an instance in which a trial is an eye movement. It's an eye movement that is nested within a person, and it's nested within a particular picture. And so we're looking at how fixation duration changes over time. So at 1 second, the slope is a positive 14. So it is, fixation duration is growing by 14 milliseconds a session at session 1. But over time, what happens to it? Which pattern is this? Less positive. Less positive by how much? And don't say 1.3. Times 2. Hey, we got it. Now, given that time is purely within persons here, everybody gets the same 6-second interval to look at these pictures. The variance component that should have been reduced by change over time is the residual, and indeed, I got 1.4% of it. So that giant pile of 94% of the variance, I got 1.4% of that. So that's why I have a little sad face. I then added a random effect of linear time to the person line. It's significant. I'll just go ahead and spoil the story for you. So that means that people differ in the extent to which they increase in fixation duration during the picture viewing. I then added a random quadratic, found the same thing, and there were no random effects of viewing of time on the item side, so we didn't include those. And here's what happens when we started add group. When you see this, folks, covariance parameter values at last iteration, and that's